Any questions? Okay, so let's do the following. Last time we looked at the character of the standard representation of S3 tensor itself, and I claimed that because of the calculations we can do with the character, we can say that this representation decomposes in a certain way, and I like to do the calculation by hand so we see the difference and how much simpler it is to work with the characters. So we start with V as the standard representation of S3. We can take this concretely to the vectors of length 3 whose sum is 0. And we can take a basis fix the basis to be these two vectors. Right, so vector space dimension 2. And we had our two elements tau are the cycles 1, 2, 3 and sigma the cycle 1, 2 in S3. And you can see the action of each of these two generators on our vectors. So tau will be 1 and tau will be 2. Recall how this goes. We cycle with the third one going to the first place. So this is 0, 1, minus 1, and this is minus 1, 0, 1. Which we could see that this is V2, and this one we can write in terms of V1 and V2 as minus V1 minus V2. Right. Yeah. So that means that the matrix, so tau in this basis maps to the matrix with entries 0, 1, minus 1, minus 1. And if we look at what sigma does, this permutes the first coordinates. This in terms of V1 and V2. So this is minus V1 and this is V1 plus V2. So sigma maps to the matrix with entries minus 1, 0, 1, 1. And just for to keep things in shape, we can check if we did this right, at least a small check. We compute the trace of our matrices, and we see that the trace of tau is minus 1, the trace of sigma is 0, and the character chi of V, which recall is the function that gives you the traces of the elements, but the trace only depends on the conjugacy class. So if I list this in the order that we had for our character table, namely 1, sigma, and then tau, the values of this should be 2. and this should be 0, and this should be -1, which is what we have. Recall that chi of v is chi of the sort of defining representation minus the trivial. So the defining representation is S3 acting on 1, 2, 3, and the defining representation on some G is the number of fixed points. Because it's a permutation representation. So the identity fixes 3 things in the set 1, 2, 3. So 3 minus 1 is 2. The character of the trivial representation is always equal to 1 for all G. So 3 minus 1 is 2. This fixes the element 3, so fixes one element. 1 minus 1 is 0. This fixes no element, so 0 minus 1 is -1. So that we did this before, just checking that this we're doing by hand, explicitly computing the matrices in this representation on this particular basis that we picked basically randomly, and we verified that things are matching. So one reason to do this, well, 2 reasons. I want to now compute what happens on the tensor product of V with V. So just as a bit of an exercise on tensor products, since I don't want to get too formal into the definition, at least give you a sense of how it works in practice. That's one purpose. And the other is to highlight that when you work with characters, things are fairly simple, and it becomes a question of fairly simple linear algebra. But that is sort of a reflection of what happens at the level of the actual matrices in your representation, and it's powerful enough that allows you to, for example, decompose a representation by just dealing with the characters. But that is not the same as actually having the matrices. So you could have situations where dealing with the characters you can, and it's really straightforward, but to go back and do the same thing that this is telling you at the level of matrices may be pretty hard. Anyway, in this case it's okay because it's all fairly small, but although the 2 things mirror each other, this one is typically much harder to deal with, to discuss, to consider specific matrices, the concrete way in which a representation takes place. Okay, so this is just V, our standard representation, and what I like to do is somehow basically repeat this exercise with V tensor V. So I said a bit of a way to get a good sense of what this means. So we chose a basis, and this gives rise to a basis for this tensor product, and it's basically everybody tensor everybody else. So let me organize it in this way. So I have 4 vectors. Four simple tensors that are going to be a basis for my tensor product. And the operation that goes, the operation tensor, this product here, is a bilinear map. So I can use that to operate with tensors. So let's see, I wish I could keep some of this, but you have it in your notes, so you'll have to refer to them. So what I'd like to do now is see what tau and sigma do to these tensors. And the general recipe that I think I already mentioned is that in general, if we have two representations V and W of a finite group G, then we define in the tensor product a representation by saying what, so we have if we have a pure tensor and G an element of G, then G acting on this pure tensor is defined as the pure tensor, or rather the tensor, the pure tensor given by, you act on V by G and you tensor it with acting on W. Okay, so let's see what tau of V1 tensor V1 is. Right, I'm going to write the matrix of tau in this acting on this V tensor V. It's going to be a 4x4 matrix now. The vector space has dimension 4. 4 is 2 by 2, the dimension of each factor. And so by this definition, what I have to do is tau of V1 tensor V1. Now tau of V1 is V2, you can check in your notes. So this is simply V2 tensor V2. Yeah? Tau of V1 tensor V2 is V2 tensor tau of V2, which is minus V1 minus V2. Right? Now, this tensor symbol is bilinear. So, this is minus V2 tensor V1 minus V2 tensor V2. Okay? So, you should maybe emphasize and notice that these two vectors are different. Right? This is not commutative. The tensor in one direction is distinct from the tensor in the other direction. Okay, tau of V2 tensor V1, same thing, is minus V1 minus V2 tensor V2. So this is minus V1 tensor V2 minus V2 tensor V2. And finally, tau of V2 tensor V2 is minus V1 minus V2 tensor minus V1 minus V2. And this, again, this tensor symbol is bilinear, so you just expand as is using the usual rules of distributivity. Scalars coming out because of bilinearity. So minus, I have to do minus V1 tensor minus V1. So that's V1 tensor V1, the minus signs cancel. Minus 1 minus V2 and so on. So I get the sum of all the terms. Okay? So with this, then I can write down what the matrix is for tau in this representation, in this basis. I just erased. So we get that tau maps to, why don't you tell me what's the first column?
We need to put the order just to...
Yeah, the order is the one I chose. I'm going to keep the order. The basis comes with an order. If you write a matrix down, you have to keep the order, right? You have to decide what order it is that you have. yeah, this vector goes to the last vector. So the first column is 0, 0, 0, 1. Second one, 0, 0, minus 1, minus 1. Third is 0, minus 1, 0, minus 1. And the last is all ones. Yeah? So in this new representation of dimension 4, tau acts by this matrix in this basis. So I'd like you to spend a few seconds staring at this matrix. See if you can tell me how I could have constructed it without going through all of those calculations.
We have minus the representation of I down there at the right left corner.
Yeah, I'm back asking something just about this matrix for a moment. Our goal is to understand this representation.
Yes, there is one block which is just the copy of the representation of T in the two-dimensional case, but with a minus sign.
Okay, that's good. So it's a bit more.
Yes, and the one above it is the same thing, and the one left it is exactly the representation.
Oh, so it's so there are 4 blocks, and the blocks is 0, 1, 1, minus 1, and somehow we're the first. So the matrix is 0, 1.
So the matrix in the original representation, V, right? In the standard representation is this.
Yeah. So we're this is 4 times we're block multiplying this into the same matrix. But
Right,
making
so-
it 4 by 4.
We can think of this as made out of blocks. Yeah? And each block, what you do is, here we have 0, and you replace the 0 by 0 times the matrix. But since it's 0, you just get 0. The second block is you take this number and you multiply the matrix by this number. And the same with this, and the same with that. And that is what's called the Kronecker product. In this case, the matrix by itself, but in general, you could do this with any 2 matrices. And it is simply the tensor product of this matrix with itself. So is everybody clear how this was done? It's sort of like Russian dolls, where you have a matrix and then inside, the entry of a matrix, instead of being a number, is itself a matrix. Well, scaled by the corresponding entry of the other one. So this is what happens in general. These matrices in the tensor product become simply, well, naturally the tensor, what we call the tensor product of the matrices, but somehow Kronecker defined it before all the fancy stuff, and so we get the name of Kronecker Product. Okay, well, you can do the same with sigma, and it'll be essentially the same calculation, so skip it, and you'll find the same thing is the matrix of sigma, I recall, in the original was minus 1, 1, 0, 1. So you get the Kronecker product of this matrix with itself. Is the the matrix in the upper left is the same matrix multiplied by -1. The second block is the matrix multiplied by itself, multiplied by 1, this one multiplied by 0, and this one multiplied by 1. So this is the Kronecker product of the matrix -1, 1, 0, 1 times itself. Okay. So let's compute the trace. Tau. Now I'm abusing notation. Tau means in this new representation dimension 4. So this is this new representation. So the trace is just 0 plus 0 plus 1. So it's still plus 1. And the trace of sigma is still 0. 1 minus 1 minus 1. And if we computed the trace of the identity will just go to the identity and the trace would be 4. So the character of the tensor product representation in the notation that we've been using is still 0 and 1. And you can see that if you compute the trace of this matrix by summing the entries to the diagonal, you will have to sum the traces of the blocks. Each block is a copy of the original matrix times a scalar, which is the entry of the old matrix. And so what you'll see is that this, in general, is the product of the characters. Okay, because if G has matrix, let's say A with entries A and J on V, and matrix B equals B KL on W, then the matrix A tensor B will be a matrix which has blocks. And let me just write down one of the blocks. This will be A11 times the matrix B. The other blocks, this will be A22, the matrix B, until we get to A and N matrix B. And if you compute the trace of this matrix, you'll have the sum of the diagonal entries will be A11 times the trace of B plus A22 times the trace of B, and so on. So the trace of A tensor B is the trace of A, or maybe let's spell it out. It's A11 times the trace of B, dot A and N trace of B. And this is the trace of A times the trace of B. Yeah, trace of B comes out as a common factor, and then you have A11 plus A22 and so on. That would be A and N. Okay, so this is a key thing to remark, and we can just verify it in our case. The trace in the character here the trace of sigma minus 1, and sorry, so tau is minus 1, the trace sigma is 0, we take in the tensor product of this representation with itself, so we would have the trace is the square of minus 1, which indeed is 1, and the trace is square of 0 is indeed 0. And the identity, we didn't write it down, but the trace of the identity here is 2. And certainly this 2 squared is 4. So it matches the values that we see here. I mean, this is not, of course, a verification that we did the matrices correctly, but at least it's a little check that we're not completely off. The traces of the matrices that we found do match this statement, that is the general state. So, this, okay, so what we've done is produce a concrete description of how the group S3 acts on this 4-dimensional space, V tensor V. We have the matrices, at least for the generators. If we want the matrices for the other elements, we have to multiply them. But we did by hand, we had a way to decompose our representation into irreducibles for the case of S3 by hand. So just to finish this calculation, why don't we try to actually do that decomposition by hand. So what we did on Friday is say, okay, V tensor V is isomorphic to some copies of the trivial representation, some copies of the sign representation, and some copies of the trivial, of the standard representation. Okay, and so by this I mean U, here it's some U 8 times and so on. Maybe sometimes people write something like this: A, here it's some B, here it's some C. And what we would like to know is what is A, B, and C. I mean, by if we look at the character of this, on both sides, the character of a direct sum is a sum of the characters. The traces add up. So we will have to have this. And what we did last time is just stare at the character. This was character 401. And we just by hand wrote it as a sum of characters of the 3 reducible representations that we have. And we found that there was only one way to do that. And it gave us this decomposition, yeah, at the level of characters. There was a unique way to do this, and that's because the characters are functions that are linearly independent, and in fact are a basis of the space of class functions. So we have guaranteed to be able to write this thing down, and by being a basis and by being linearly independent, is a unique way. So what I claim is that this, and we'll prove eventually this, a decomposition at the level of characters corresponds exactly to a decomposition at the level of representations. So this, we'll see later, necessarily says that this decomposition that we're looking for has no other option but being this one. Not equal, but isomorphic. Okay? So let's check the dimensions this has dimension 4, this is dimension 1, this is dimension 1, this is dimension 2, so it looks good. So now what I like to do, and this is what I was saying earlier, this is in general not an easy thing to do. I actually want to find this decomposition by our bare hands. So what this is telling us is that in the space of dimension 4, V tends to V, there is one one-dimensional subspace, a line, that is completely fixed by the group. There's another line that is acted on by the sign, so tau acts trivially and sigma changes sign. And then there is a two-dimensional subspace in which the action is just the same as on V. Okay? So I like to actually identify these spaces. So how do we do that? How do I identify what this U, for example, is? Or this copy of U, this line that is fixed by the whole group?
You have V1 tensor V1?
No, that wasn't fixed. Sigma takes it to, tau takes it to V tensor V2. V2 tensor V2. We did this abstractly before, so maybe the first class or second class.
The sum of the 4 will be fixed?
No. Why should it be? Maybe, but I don't see why it should be. Well, the general recipe that we outlined for this example like this.
We can take some vector and conjugate it by each element of the group. Somehow might be fixed.
Yeah, I could try that. This is a general recipe. If you want to find something fixed by a group action, as long as you can make sense of adding, you take the element and you add to all of its conjugates. Of course, the drawback of that is that you may work all this hard to do that, and then the sum is 0, and then you're stuck because you haven't done anything. No, the recipe. Well, I mean, you could try that, but to follow the recipe that we outlined before, what we said was, why don't we just look at tau it's alone? Tau is an element of order 3, and so when is acting on a 4-dimensional space, we argued that it is diagonalizable. All elements of finite order are diagonalizable. All matrices of finite order have to be diagonalizable in characteristic 0. And so this space, V tensor V, decomposes as, let's see, what notation will I use now? I'll use U and U prime and so on, like here. Decomposes, maybe I'll say this. I'll write it as W1, W theta 3, W theta 3 bar. Where these are eigenspaces for tau. So if we're looking for a line that is fixed by the whole group, it has to lie in this space, because these are vectors in these other components are multiplied by the cubic root of unity. So let's say the 3 here, let's say here is e to the 2 pi I over 3. So to find the line that is fixed, we would have to do this decomposition, and we either do it by hand. It's not so large, you could just do it by hand, or you can put it in your computer and find that out, which is what I did just before coming. And so you'll find that this vector u, if I did this correctly, maybe we should check. This vector is actually fixed by tau. And in fact, so what happens is that this vector space has dimension 1, this is dimension 1, and this is dimension 2. So we get two basis vectors for W1. So they span W1. And U prime is V1 tensor V2, and it's V2 tensor V1. Okay, so why don't we check? So this I just did, as I said before, coming from using the computer. You just write the matrix down and ask for the eigenvectors. The eigenvectors are going to be in this field. I mean, they will involve this cubic root infinity in general, but here, when the eigenvalue is 1, they have rational entries. So let's just, for example, check what happens with this vector, which is looks a little easier. So let's check what does tau do to this. I'll look at my notes. So V1, V2 goes to minus V1 tensor V1 minus V1 tensor V2, and V2 V1 goes to minus V1, minus V1 tensor V1 minus V2 tensor V1. So indeed, these two things cancel, and we get minus V1 tensor V2 plus V2 tensor V1. And this is minus V prime. Yeah. So tau, no, that's not. What should I? It's not. Oh, that was copying sigma. So sorry, this is sigma. I anticipated because sigma will have to preserve these pieces because of how they. So what we did was say, okay, rho tau, they don't commute, but rho tau is the same as tau inverse rho. So sigma of W 1 is W1, and sigma of W theta 3 is W theta 3 inverse, and similarly, say 3 inverse is theta 3. So sigma permutes these two eigenspaces, and it fixes this one. And so these two vectors actually span W1, but sigma, one will see sigma fixes the U and changes sign to U prime. So to do tau, so I'm not going to do all of the calculations. You can check this. Maybe I can give it as a homework problem so you actually repeat this on your own. It's the best way of understanding things. So let's see what tau of U prime is. V1 tensor V2 goes to minus V2 tensor V1 minus V2 tensor V2 according to what we did. And then V2 V1 goes to minus V1 tensor V2 minus V2 tensor V2. And so we get V1 tensor V2 minus V2 tensor V1, which is in fact V prime. So tau fixes this vector, sigma changes sign of it. So this line is actually, it gives you a representation of the group S3 isomorphic to U prime, to the sign representation. And this other vector, I mean it'll be a little longer calculation, is first of all fixed by tau and also fixed by sigma. So this W1 subspace breaks up into two pieces spanned by U, the little vectors little u and little u prime, where sigma acts trivially or by minus sign. So W1 is isomorphic, well, is W plus direct sum W minus, where W1 plus is generated by U and W1 minus is generated by U prime. And so W1, this is isomorphic to the trivial representation, and this is isomorphic to the sign representation. And these two pieces are both one-dimensional and are swapped by sigma. So W theta 3 direct sum W theta 3 bar is isomorphic to the sign representation. So this is a completely concrete, explicit decomposition of this representation into its irreducible pieces. Okay?
I have a question. We know that V is irreducible representation.
Yep.
But this says it is reducible because it is written as a sum of two.
This decomposition only involved tau, not sigma. So tau, if you take this representation and only consider tau, then it is a sum of one-dimensional representation because tau generates an abelian group. An abelian group only has one-dimensional representations, irreducibles. So this decomposition is a decomposition where you only consider tau. When you consider the full group, then these two pieces are not in fact fixed by sigma, but they're swapped. So this two-dimensional space is in fact irreducible as a representation of S3. But if you forget sigma, it becomes reducible. Okay? I mean, every vector space is a sum of lines if you don't care about the action of the group. So any vector space of dimension bigger than 1 is reducible with respect to the trivial group. Yeah? So here, the non-commutativity of the group is what is making this representation of dimension bigger than 1 be irreducible. It's sort of the source of that phenomenon. So I insist, abelian groups have only one-dimensional representation. So every representation of an abelian group is a sum of lines. But that's far from the truth if your group is not commutative. Okay, so maybe I'll outline this as something for you to work out on your own. And I think it's a good exercise to try to familiarize with all the various constants. I mean, it's one thing to do things abstractly, but it's good to go down to some examples and test how well the concepts are clear in your mind. Okay, now we're going to do another construction of linear algebra, which is HOM. So we have two vector spaces, V and W, again, finite dimensional and over C. We have the notion of linear maps. These are maps from V to W, which are just linear. And this is itself a vector space, since you can add linear functions and you can scale them. So any construction of linear algebra will have a parallel in the world of representations. So we would like to make sense of what should be the G structure that we're going to give to Hom of V to W when V and W themselves are representations of a finite group G. Okay, and for this, what we're going to do is appeal to things that we have already done. So in a certain sense, all the constructions of linear algebra that we're going to consider, the structure as representations will come from the things we already did. So concretely, what I like to use is that this vector space can be described in terms of the tensor product and the dual. And the dual and the tensor product is something we already discussed. So the claim is that we can describe the linear function maps between the spaces V and W in terms of the tensor product and the dual. Okay, and the way we can do this is as follows. If we have a dual vector V dual and a vector W, we look at a simple tensor. We're going to associate to that a linear map. And again, this is one of those things where if you're asked to do this, you just put the symbols in the only order that makes sense, and that's the answer. So I have to somehow associate to this a map from V to W. So I give myself a V, and I have to produce a W. Right? So I have a V, and I have to map it to some W. And what I have as an input is a dual vector V star and a vector W.
This
So
star V multiplied by W?
yes. So V star V is a scalar, and it makes sense to multiply W by it, and W is in W, so this at least is a meaningful thing. Giving a V, we produce a vector in W. And the claim is that this is actually an isomorphism. So in particular, so we would have to check a number of things. We have to check that this association V to this is actually linear, but that would be a simple consequence of the fact that V dual is linear. Yeah, so I won't write it down. And then the thing with a little more weight is to show that this in fact is an isomorphism. Rather, this gives rise to a map. Any element in here is a sum of these pure tensors, and I extend this definition to the sum in a linear way. So let's do this concretely using bases. Let's say, let me sketch a proof. Let's say V1 up to Vn is a basis of V, and W1 up to Wn is a basis of V. This is a basis of W. A basis of V gives rise to a dual basis, V1 dual. This is a basis of V dual, which has the property that applied to the original basis gives us 1 or 0 in this way.
Sorry, in a finite dimensional space, the dual is the same as the space, right?
It's not the same, it's the same dimension, so it's non-canonically isomorphic to the original. Yeah? This is a way to do it concretely. The claim I'm making here is that there is a basis. Well, in fact, this defines for us Vi star. The claim is that that is actually a basis. So V and V dual have the same dimension, but they're not canonically isomorphic. It requires a choice. V dual dual is isomorphic to V in a natural way. Okay, so what I like to do is we have a basis of V tensor V dual tensor W, namely Vi dual tensor Wj. So let's see what homomorphism this recipe gives. So this is a map from V to W. So let's see where does it take a vector V sub k of the basis of V that we chose. It maps it to, the recipe is we evaluate the Vi dual on it, and we multiply that result by Wj. So this is our map. But this, because of the choices we made of a dual basis, this will be 0 unless I is equal to k. So in general, we'll get 0. If I is equal to k, Vi dual of Vi is 1. So this is simply Wj. So what map have we produced? The map that takes the kth basis vector of V to the jth basis vector of W. And to give a map from V to W, if we have chosen basis, is just to give, you have to tell where the basis vectors of V go to. So if we have a map from V to W, so if V goes from V to W is a linear map, then phi of Vk, or V, maybe let's say, let's do this right here, I is equal to k, so let me say I is some linear combination of the basis vectors Aj, Wj, from 1 to m. So let me call this linear map if I want to give a name or not. We'll call this thing let's call this Vij. So this is sum of Aij, Vij of Wj of Vi. Right? Because Vij, maybe I should have called this something else. Let's use the K. Yeah, now it's okay. So this Vij of Vk is exactly equal to Wj when I is equal to K. So this is sum from I equals 1 to n, sum j equals 1 to m. So basically what we're saying is this Ij, so if you want to think of things in matrices, what does Vij do? It takes the vector Vi and takes it to the vector Wj. So it's a vector, it's a matrix that has zeros everywhere, and on the ith column has a 1 in the jth spot, right? Because it takes the vector Vi to Wj and everything else goes to 0. So this Vij is nothing but this matrix with exactly a 1 in the ij spot. And so what we're saying here is any map from V to W is a matrix of n columns and m rows, and any matrix is a linear combination of matrices like this. So phi is some matrix A, so it's given by matrix A of Aij's, and this is simply Aij times the matrix with a 1 in the ith in its place and a j. So any matrix is a linear combination of matrices which only have a non-zero entry in the ij spot. Yeah? So this shows that this is an isomorphism because any phi
But what is K?
uniquely determined by this. A K is arbitrary. K from 1 to n. Oh, basically all we're doing is, let's see if I want to think of something concrete. So if you have a matrix 1, 2, 3, 4, 5, 6, I'm writing it as 1 times the matrix 1, 0, 0, 0, 0, 0, 0, plus 2 times the matrix 0, 1, 0, 0, 0, 0, and so on. And each one of these matrices that have only a 1 in the ij spot is exactly what we achieve by this map. Yeah. So there's n times m such matrices, which is the dimension of the linear space. Okay, so maybe you should work on this on your own. It is one of those things that is not hard, but it may take a little digesting if you're not familiar with these things so well. Yeah, so the point, so the dimension of HOM EW is the dimension, is dimension of V times dimension of W, and the same of course holds for V dual tensor W. Each factor has one, the first one has dimension n, the second one has dimension m. Okay, so the point of this story is that we would like to make sense of Hom of VW as a representation of a group G if V and W are representations of the group G. And so by this isomorphism, there is a natural thing that we should do. And so define a G action on Hom via this isomorphism. In other words, we already know how G is supposed to act on V tensor, V dual tensor W, and we transport that into Hom by this isomorphism. So let's chase now. What does that mean? Concretely, if I have a linear map, how is the group G supposed to act? And at the end of the day, you can forget all of this discussion and say, okay, well, I'm happy. This is how it's supposed to act. This is what I'll remember. So let's say we have homomorphism from V to W, and which is of the form of corresponding to some pure tensor. Just to, because it's easier to describe here. And would be enough to, the conclusion we're going to draw will be one that then will apply to any phi, but it will be enough to do it here, because pure tensors generate the whole tensor product. So what should G of phi be now? So this is we're going to change all these symbols. It's supposed to be a new linear map. So maybe I'll say this. So phi corresponds by assumption to V dual tensor W. Now we want to know what it corresponds to. And what we said is that we're going to transport the way G acts in here to Hom, what the French call transporter structure. We know how we're supposed to act on the tensors, and we're going to transport that back to the homomorphisms. So let's see how what is this thing going to correspond to? So let's look at this one first. Recall that the way we define the action on the dual is that if we compute the value of this new thing on V is the value of the old one evaluated in V. Yeah. So G V dual tensor GW is so if we so G phi of a vector V, we're supposed to compute G V dual of it and multiply by G of W. This is the recipe for any pure tensor to find out what it corresponds to. by the previous observation, this is V dual or G inverse of V times GW. Now this thing is a scalar, so I can commute G with it. Yeah. Now this thing here inside is exactly phi evaluated at G inverse of V. So this is G at G inverse of V. So the conclusion is that G phi acting on the vector V is G of phi of G inverse of V. Okay. Now, so if I write this as a diagram, I have V goes to V by phi. We can just summarize it in this diagram. Sorry, this should have been W. So this is the final outcome. We checked it on pure tensors, but that's enough to be valid on every tensor product. So this is this statement. So so we have to maybe understand exactly what this means. G acts both on V and on W. These are completely different vector spaces. So these symbols carry a whole lot of meaning. Here, G acts on the vector V the way it's supposed to act on vectors of V. But here the G is acting on the value of phi on this vector, which is somebody in W. So this dot that I'm not even writing is not the same as this dot. This is the one on V and this is the one on W. Okay? But the summary, it is simpler to write that. I should write rho of G and maybe psi of G and so on. But it's just easier to.
I'm sorry, how should I read this diagram?
That this diagram is commutative. All of the arrows are linear maps. But I'm abusing notation a little bit. This would be rho of G, and this would be maybe rho prime of G as some other representation. And so what it's saying is if you want to know how to go from V to W, you can go up, which is given by the inverse, and then apply phi, and then apply G. So this is what all of this thing is written up in one line. Okay? Yeah? Okay, so notice that if W is dimension 1, so W is dimension 1 with the trivial action, then phi from V to W is just the hum of V to W is isomorphic to the dual vector space. And this definition is compatible with what how we define the G action on B dual. The point is that if G acts trivially, then you can ignore it, and that's just how we define the dual representation. Now, so with some pains, we now can talk about Hom of V to W as a representation, if V and W are representations, in a natural way. We want to define things in a way that everything is compatible with natural maps between things. So let's look at this, because it's a representation, is isomorphic to, well, we haven't proved it, but we will eventually, representations where UI is an irreducible representation. Yeah? And we'll be interested in decomposing this. Among the reducible representations, we always have the trivial representation, and this corresponds to the vectors inside the vector space that are completely fixed by the group action. So these are linear maps that are fixed, so such that G phi is equal to phi. Now let's actually compute what that means in terms of the action, because we describe the action explicitly. So what does it mean for phi, G phi to be equal to phi? Well, they both have to agree on every vector v. But then so here again, you have to be careful with all these notations. Here G phi means the action of G on the homomorphism. Yeah, so to be precise, I should write this like this. Now G of phi on a V is G of phi of G inverse of V. For now the symbols mean a different thing. This means G acting on the vector W, whatever image of phi is. So we want this to hold for every V. Okay? Now I can change V to V inverse to G inverse of V, and let's say V1, this is phi of G V1, where V1 is G inverse of V. And if V runs over all vectors of the vector space, so does V1. So the conclusion is that this holds if and only if and this holds, which means that phi is G linear. In other words, if I act on the argument of phi by a group element G, I get to take it out of the argument. And again, I insist that this is a very concentrated way of writing it, because here G means acting on the V way, and this is G acting on the W way, which are completely separate vector spaces, but the map preserves the way G acts on both its source and its target. So what we can conclude is that this subspace, and we'll use this notation, seems like a tautology, but the meaning of the G down here is to say that is G linear, just a definition. So being fixed by the group G in the way we define the action turns out to be equivalent to being G linear. Okay, and okay, so we'll see that this this discussion with Hom will turn out to be very useful for our understanding characters. And we'll come back to that. Yeah, so one other thing I should mention, since we computed define Hom in terms of tensor products, and we know how the characters of tensor products and duals work. So note that the character of Hom of V to W, thought of as a representation of G, is equal to what?
The conjugate of the character of V multiplied by the character of W?
Yes. So the dual gets a conjugate, and the tensor product is a product. Okay, so let me start with something, and I'll continue on Wednesday. So, what I want to get to is the decomposition of a representation into reducible. So, first thing will be to consider this projection formula. So if we have a representation of G, as we did just now with Hom, we consider the subspace of vectors that are entirely fixed by the group G. This is a subrepresentation. And what I like to describe is a way to project from the vector space V to this subrepresentation. So V to V, I'm abusing notation now. I hope it's by now clear what this means. We're given a representation, so it makes sense to talk about G as a linear map from V to V. I don't write rho of G anymore. So this is linear by definition, but it may not be G-linear. Okay, it will be G-linear if it computed with all the other ones, but typically this will not be the case. So I guess that was something suggested earlier. We can take this linear map and try to produce a G-linear map by averaging. So let me define this, call it phi. So each G is an invertible map, linear map from V to V. Think of it as matrices if you like. So I can add them as endomorphism, and the result will be some endomorphism. Okay, so if you think of G's as being matrices, this is we're summing all these matrices up, and there will be some matrix. And here it will be for the formulas to come out right, useful to take an average, so divide by the order of the group. And if you try to do this, suddenly if an infinite group, you will have trouble making sense of this immediately. And you would also have trouble making sense of this if, for example, the characteristic if you field divided the order of the group. And that's, in fact, when the whole theory changes completely. But we're working with a complex number, so we have no trouble with the meaning of this. So what I claim is that this is, in fact, this map is G-linear. And the proof is simply that if you conjugate, so you have an H in G and you do H phi G H inverse, you're just going to rearrange the sum. This is the standard argument. This is H G H inverse. And if G runs over the elements of the group, so does H G H inverse. So this is just the same sum again. And so this is the same as phi. So this means that if I do phi of H, well, I could have put the inverse on the other side. Phi H of V, this is the same as H of phi of V. So it's G linear. So what I'd like to show now is that this map phi, in principle, is a map from V to V, a linear map from V to V, but in fact its image is in V upper G, that is the vectors that are fixed by G, and moreover this is actually a projection in the sense that phi composed with phi is equal to phi. So if you give me a vector in V and apply phi to it, you're going to get a fixed vector, and every fixed vector appears this way. And if you apply this map to a fixed vector, it stays put. So let's prove this. Let's say we have a vector W and called V phi of W, then this is by definition the sum over the conjugates, or translates rather, of W. So let's compute H of V, same type of argument, this is the sum over G of H, G, W. I guess a priori I should say I have this, but by the whole compatibility of these symbols, this is the same as the brackets being here. And if G runs over the elements of the group, so does H times G. So this is the same as V. So for any H in the group, the vector V stays fixed. Okay? And if V belongs to the fixed subspace, then phi of V is clearly equal to V, because each one of these terms we're summing G of V, but G of V is by assumption the same as V, so we're adding the vector V as many times as the order of G, and then we're dividing by that order, so that gives us back V. So that's why you see this factor 1 over G appearing. So that means that the image is the whole thing, because what is an element of V that maps to a given fixed vector? Well, the fixed vector itself. And so if you compose phi with phi, you in fact get phi again, because phi maps to a fixed vector and the fixed vectors get sent to themselves. So this is a projection from V to this sub-representation. So now let's compute the trace of this endomorphism. Phi is a map from V to V, so we can talk about its trace. The trace is an additive function, so this is, by definition of phi, the same as the trace of G acting on the representation V, but that's what we call the character of V. So we get that the trace of this endomorphism is equal to the sum of the character values, or rather the average of the character values. Now, notice the following. Suppose now that V is irreducible. Then what can we say about V sub G? It's a sub-representation, so it has to be either 0 or V. Right? And what case do we have? What case? When do we have one case or the other?
You can use Schur lemma here.
Sorry?
Schur lemma.
We're getting there. We don't need it yet. what does it mean that V of G is equal to V? It means that G acts trivially, right? And in that case, the dimension has to be 1, right? So we can be a bit more precise. We're going to get 0 if V is not trivial. And we get 1 if we get the whole space V, if V is trivial. Trivial means the trivial representation, so it's a one-dimensional representation with the group acting trivially.
I'm sorry, why does it have to be 1? What has to be? Why does it have to be dimension 1?
Because if it VG is a sub-representation where the group acts trivially. If it's equal to the whole thing, it means that the whole thing is trivial. Right? V of G, by definition, is the set of vectors such that the group fixes them. If that's the entire thing, it means that the representation is trivial. The group doesn't act. Well, it acts by doing nothing. Okay? Let's see. I forgot to make another point here more clearly. What can we say about the trace of phi? Phi is a projection. Yeah? So, what is its trace? So phi goes for V to Vg, which is a sub-representation. So V has this decomposition. We know that every sub-representation has that complement. So if I decompose phi in this manner, what is it going to look like? Well, it's going to be the identity of some size followed with 0. Yes, because in every vector here, it is fixed. So phi of V, now it's a projection, so phi of V is V. And the vectors not in the complement will have to map to 0. So the trace of phi is actually equal to the dimension of Vg. Okay, so I think we should stop here and continue on Wednesday, because we want to use this in a serious way, and to do justice to this, it will take a little time. Let's keep this in suspense. I'll come back and review this last discussion.